Right, so we are in the middle of this proof. So we are trying to prove this theorem, which says that if for a degree d polynomial you have a size as circuit, then you can squash that high depth circuit to depth 3. Okay, so this will be a sigma pi sigma circuit in the end, where the bottom sigmas will only be adding square root d many things, and overall size will be very large. It will be s to the square root d, but this is still interesting because it could have been s to the d, right. So this is much better than the trivial bound. So in a non-trivial way, you can reduce depth all the way down to 3. So this we will prove in kind of 4 steps. So the first step is step 0 is squash it down to depth 4, that we have already seen. Then step 1 is replace these product gates by sum of powers, right. That it is called Fisher's trick, and this also we have seen. Then step 2 is convert this powering gates or wedge gates to some other special form, right. It will be write a power as a sum of product of univariates, and since these are univariate polynomials, you can factor them over complex. So you can actually write power in this special form. Now it may not be clear why this is enough, but this will be enough. Okay, so let us go slowly through this step, and then how this is used. So we want to convert R fan-in pi gate to sigma wedge sigma. So this is already done, that is clear, and it gave us this sigma wedge sigma depth 5 basically. Right, so the step 2, actually I want to talk about step 2, which is this. So now wedge sigma we can convert to sigma pi sigma using this duality trick, right. So this duality trick is basically this identity that sum of zi's power v can be written as sum of product of univariates, where all these univariates are essentially the same. It's the same polynomial fi evaluated on these different s variables, right. And the proof was just by looking at, so look at this auxiliary polynomial and from this extract the coefficient of t raised to s minus 1. Well, not exactly here, but here in this. So in this f minus t raised to s raised to b, you extract the coefficient of t, basically the leading coefficient, right. Extract the leading coefficient, and that you can do by interpolation. So if we have time in the end, we will work out the interpolation formula, but at this point it is intuitive that if you have a polynomial of low degree, then very efficiently you can extract whatever coefficient you want. So that is exactly what is happening here, and that will be of this type, right. The dual expression here is what you will get when you expand it out. So you exactly get this. So you actually can write sum of zi raised to b as sum of products of alpha I plus zj raised to j. So alpha I plus zk raised to j. Okay. So this is the thing you should remember. So this is a very simple identity, but the point is that a priori it is not clear why we are doing this, right? This is just, we are just reconverting powers, but what is the use of this? So that will happen in the last step. Okay, this is where we stopped. So the beauty of this is here. Now if you are given power of sum of powers, right? So let us say you are given this sigma zi to the a whole thing raised to b, then the previous identity will hold as well, right? So you will get these expressions, alpha I plus z1 to the a raised to j, and multiply these things and then add them, right? This small representation you will get, and so that explains this much, right? In the sigma wedge sigma expression, the middle part has been expanded this way. So will it make any difference if you attach a sigma on top? It won't, right? So this sigma is also fine, because this just gives you more summands, that is fine. So all we have to now analyze is this sigma, the inner sigma, right? So what is the effect of the inner sigma? Inner sigma is like replacing z1 by a linear polynomial, right? So you have now, because of that, so this innermost sigma gives us, it continues to give us something easy, right? So this is just sigma gamma ij alpha I plus a linear form L1 and or a linear polynomial, even a linear function ls raised to a raised to j, right? So these are linear polynomials, but this hardly changes anything, because we can still factor this completely, right? Alpha plus L to the a still factors completely over the complex field. Why is that? Well, whatever was the factorization with z1, in those factors, instead of z1 just put L1, right? So they remain linear factors. So this thing actually completely factors, completely splits over complex or algebraically closed field. Is that clear? So you get how many factors? So this summand will factor into s times a many linear polynomials, right? It completely splits with. So do you need the full power of complex numbers here? What do you need from complex numbers so that this thing completely factors? Suppose alphas and li's were all just integral, or maybe rational I mean their coefficients were rationals, right? So then what is the number that you need in your field so that these polynomials completely split?
Or rational integers. I mean,
No, yeah, so rational integers, sure, yeah,
algebraic integers.
yeah, but even more special. So you just need for this you will just need q of, yeah, let's say q of zeta 2a, because the point is
You might need the roots of all the integers also, right?
yeah, you also need those actually. No, so okay, what we can do, uh, what are these alpha i's? Let us go back. How did the alpha i's come into the picture? We chose them. So here actually choose alpha i's to be eighth powers. Right, because we just need in the interpolation formula we just need enough distinct elements in the field, so we can take them to be just eighth powers. Let us say we take the first eighth powers, as many as we need. So these are alpha i's. So which means that so now let us come back here. So here alpha i's are in fact let us take minus alpha I to be, pick minus alpha I to be eighth powers. So then here in this expression since minus alpha I is an eighth power, all you require is zeta A, eighth root of unity, to do this factorization. Okay, so zeta A is just the eighth, a primitive eighth root of unity, which will be usually, almost always it will be a complex number, but these are enough. Is this clear? Right, since alpha i's are or negative alpha i's are eighth powers, to factorize this thing you just need all possible eighth roots of unity, and for that you just need one primitive root of unity that generates everything. Right, so it is just this simple extension you have to go to, q zeta A, and there you have an expression. It's a sigma pi sigma expression. Yeah, so this discussion implies that more precisely sigma wedge B, sigma wedge A, and in the bottom sigma we had, currently we had just one variable, so let's call this 1, this sigma 1 circuit can be expressed as a sigma pi sigma circuit where the bottom sigma has fan in 2. This can be expressed as a circuit of depth 3 over q zeta A of size okay, so who can mention the size after all these transformations? I think it is something like S times A times B and slightly more than that, S cube A B square size. Okay, so let us not worry too much about these this exact bound. It's ultimately to be polynomial in S and A and B, given the original thing size S. Okay, so size S depth 5 circuit is brought down to depth 3 of similar size. Do we agree? Any question here? Right, and this then implies that so let us, after this detour, let us go back. So what was the circuit that we had developed in the previous step? So that was C2. right? C2 was this depth phi circuit where these powering fan-ins are square root D. This is your A and B. And the bottom sigma is also square root D. So let us now depth 3 using the reduction we have just seen, and let us call that circuit C3. So we can now write that C2 converts to sigma pi sigma A plus 1 circuit. Well, A is square root D. Let us keep square root D. Converts to a square root D, or maybe slightly more, plus 1 circuit C3 over Q zeta A. Okay, I want A. So this is A plus 1 and A is square root D. Let's take the ceiling. So depending on this bottom fan-in, you have to go to an extension of, you have to go to a number field, this number field, and there you will get a circuit C3 of depth 3, that much fan-in, bottom fan-in, of size S3, okay, which is slightly cubic or slightly supercubic, S2 cube. S2 was the size of C2. Is that clear? So this is what we wanted to show. In fact, we have shown more. We have shown something stronger, that by going merely to Q zeta A, any depth, any general depth circuits C1 or C0, we can bring down to depth 4 and then depth 3, and even the fan-in, bottom fan-in will be just square root D, where D is the degree. But now it will have coefficients from the number field Q zeta A. And what was S2 cube in terms of the original size S? So the biggest price we paid was when we came to depth 4, right? So that is S to the root D. So that's the result. So size S degree D polynomial comes down to sigma pi sigma square root D over Q zeta A, and size blows up to S to the root D. So which is also the fan-in of the product gate here, right? So actually the depth 3 circuit is multiplying a lot of things. Each of the factors have kind of small sparsity. So it is, you are just adding around square root D many things, then multiplying a lot of them, and then adding a lot of them, and that gives you a very low degree D polynomial F, right? So this whole thing is very counterintuitive, but it is true. So you can come down to depth 3 in a non-trivial way. Any questions? So all that remains is a slight technicality, that since your original polynomial was a rational it had rational coefficients, and this circuit C3 has irrational coefficients. So can you now convert, can you also make them rational? Okay, if you started with if you want to compute a polynomial that is rational, then why do you need to use these zeta a's? Can we eliminate the zeta a's also? right? So that will be the last step. That will, so that is the final step 3. So C3 has coefficients in the number field Q zeta A. But eventually it computes F, which is free of zeta A. Right, so let us utilize this. To eliminate zeta A from C3. How do you do this? A circuit that is using elements from a field extension to compute something in the base field. How do you eliminate the use of this field extension elements? Why do you think it is unnecessary? Oh, Gauss lemma.
I mean, to show that it's unnecessary. At least for this Q case.
No, Gauss lemma is very pedestrian. We have come much further ahead of Gauss. No, no. So what we will do instead is
Because the coefficients of the
right.
and they are 0.
So actually, the wherever in the circuit you are using zeta A, or which includes also powers of zeta A, you replace zeta A by just a new variable. So when you do, then so this will of course not compute the polynomial f now. It will be computing something else because you have replaced constant zeta A by a formal variable. So actually the number of variables have now increased. It has become n plus 1 now. So you are now computing some auxiliary polynomial, and from that auxiliary polynomial you can recover f. Okay, so we will do that. You can recover it by interpolation, and that auxiliary polynomial is free of zeta A, essentially by definition, because wherever, I mean, you can see the circuit, so you can see where zeta A constant is being used, and just replace them by y, right? So now the circuit that you have is actually, it only uses rational numbers. Nowhere is it using anything up beyond q.
So then we can just set y to 0, right? Why do you have to interpolate?
Y to 0, that's a bad idea. You are saying that zeta A is 0.
More things get cancelled.
Oh, more things will get cancelled.
Yeah, you cannot say that let us replace number 1 by y and then set y to 0. That is like killing all the constants. Yeah, so what you will do is you will have to extract y to the a, y to the 2a, y to the 3a dot dot, because these are the powers of y that give something rational. Y doesn't give anything rational because it is zeta, it's irrational, and y square may not also. So the first time it will give something rational is y to the a, and then powers of that. So these terms you will extract, and the sum of these is f. It has to be, right? So the sum is what you want to extract. So that becomes a lemma. So let f be a polynomial over this extension, irrational extension, and variables, be a sigma pi sigma, but it could have been any circuit. That I think is not important. This lemma is nothing to do with depth 3. degree D, size S. I am calling F as the circuit. Let me do that. So F is the depth 3 circuit computing a polynomial in QX. Okay, so we are looking at a circuit that uses higher constants, but ultimately computes only lower constants as coefficients. So then these higher constants can be removed. So then there exists an equivalent sigma pi sigma circuit G which uses only rational constants. So it's all the intermediate computations are in QX bar of the same degree size. Okay, so that is the conversion from F to G without much cost. So yeah, the idea is simple. It is just that replace each occurrence of zeta AI in F by y to the I to get the auxiliary circuit F tilde, which actually has only rational constants but has one more variable. Okay, this extra variate rational polynomial, now you have an expression for this sigma pi sigma. The size hasn't changed, it's actually the same circuit, essentially the same circuit. What can you say about the degree with respect to x's? So that has not changed, the intermediate degrees have not really changed, or the upper bound remains the same. What is the degree with respect to y? How bad can y get in terms of degree? So original circuit degree bound was d, right? So it is d times what is the highest I in zeta a to the I? That is highest is a, right? So it's just that's the bound, d times a. So since f is sigma pi d sigma, so the product that happens, this product gives you degree of y not more than d times a, which is small, right? So the degree in terms of y is very small. Also, that's the important thing, that from f tilde you can recover f by substituting y equal to, well, the definition, right, y equal to zeta a. So f tilde knows about f. How do you use that? So basically use the fact that this zeta a to the j, it becomes rational if and only if j is divisible by a. Well, this may not be true I
Sound.
yeah, this by itself is not true, but I don't need this. I want to say something else. No, I think my argument should not be based on this because this is wrong. Well, what I want to conclude is that if you look at the coefficients of y to the IA in F tilde, where I varies from 0 to D, this sum is equal to F. Do you believe in this? I think easiest argument would be forget the model, just look at a simple polynomial. Let us look at the polynomial b0 bi times zeta a to the I goes from yeah, can we assume that a is a prime number? Then it will be easier. Otherwise, we have to concoct other concepts. It will not help. Let us just assume that a is prime. So, say when a is prime, then the property is that zeta a to the j, this will be rational if and only if a divides j, then it is true, right. For example, if a is 3, then 1 zeta 3 and zeta 3 square, you look at this, out of these three only one is rational, both the other two things are actually complex, right. So forget about q, they won't even get real, right. So yeah, so let's just continue with q. Right. So f tilde you can view as a polynomial in y, polynomial in y, aj is these are the functions in x, and in this polynomial when you substitute y equal to zeta a, the zeta a to the j's which will contribute, let's say, real terms, right, they will exactly be the j's that are multiples of a. All the others will contribute complex, certainly irrational terms. So these we will ignore. Okay, these we drop, and the thing that remains is this sum after dropping, and this has to be equal to f, right. This has to be equal to f because of equation 1. So this implies by equation 1 there's this second equation, equation 2, is true. Do you agree? Because in equation 1 RHS is real, and in equation Equation 2, when you look at the LHS is the part that is contributing all these real coefficients. So actually, if you want, if it helps, you can put also y IA, but not matter because it's already 1. And this is what you are evaluating at y equal to zeta a. So it is actually this part of f tilde where you are substituting y equal to zeta a, and so the sum of these coefficients will become equal to f. All the other parts of f tilde don't contribute anything. All they can contribute is 0. Right? If the other part contributes something non-zero, then that complex thing cannot be cancelled by the real things, right? And f is real. Is that clear? So that is the, yeah, once you have this equation 2, what these coefficients of f tilde, that you do by interpolation, because you have a degree bound with respect to y, individual degree of y is low, so you can just, yeah, for every coefficient you will do interpolation. So that is the summand of number of summands that you get is around dA, and on you will do it d many times, so you get AD square blow up. So all that is within our budget. So thus we could interpolate by evaluating f tilde x bar y on 1 plus dA distinct points in Q. So this yields SDA size sigma pi sigma circuit for f over Q. Right, this finishes the proof. So you start with a circuit, you bring it down to depth 4, then you bring it down to, then you take it up to depth 5, then you bring it down to depth 3, but you have gone to another ring to field extension, to number fields, so then you bring down the number field. Okay, so that's your final depth 3 circuit. So thus we get sigma pi sigma square root d circuit C4 computing C3 and hence the original polynomial over Q, and it has size s to the square root d. So completing the depth 3 chasm. Over fields of characteristic. So 0 is clear because 0 is essentially rationals proof. What other characteristics have we covered? Yeah, so the only place where we needed characteristic was this Fisher's trick, right? So there the the monomial that you convert.
The root of unity also will have to.
Sorry,
The root of unity place also will have to.
there is no root of unity. It's an expression over Q.
No, I mean if you change that characteristic,
Right.
then at some point we needed a eighth root of unity, right?
It's an extension. We never had eighth root of unity. We went up. Yeah, so the monomials that appear in your depth 4 representation, those monomials should have degree less than the characteristic. So to put it simply, we can just say greater than D. Then it will certainly work. So the depth 3 Chasm is there as long as the characteristic is either 0 or more than the degree of the polynomial you intend to compute. Yeah, more than this we cannot say, because if the characteristic is even equal to D, we don't really know what are we getting in the depth 4 representation. Maybe in the depth 4 representation we are getting some monomial of degree D, and there is some product gate in fact which is computing that monomial. So when you try to do Fisher's trick, it doesn't work. Provably it will not work. There are examples. So that is all we can say. Okay. Yeah, so that is the limit of depth reductions, right, all the way to depth 3 and decent characteristic fields. Any question at this point? What is prime power?
For A.
Oh, A. A is an upper bound.
No, no.
Just look around you, find the nearest prime. There are a lot of them. That's just an upper bound.
You could say handle it right. You just have to, depending on the factors, so if you use some roots of it, like some cyclotomy, it shouldn't be that hard to handle.
Yeah, yeah. So here I will just say, since I am on record, that pick a prime. I don't want to give you other ideas. Okay. Well, so then we will move to something quite different, but still highly interesting, which is well, so one way to reduce circuits is the depth reduction, which is quite visual. Question that you can ask: if you wanted to convert a circuit into an algebraic branching program, or let us say iterated matrix multiplication, right? So we can try to convert a circuit into that as a product of matrices, right? So what would be your first answer? So reducing circuits to EBPs or IMMs, right? Algebraic branching program, which is the same as iterated matrix multiplication. So this actually is an open question, how to do this efficiently. In poly size, right? So and the problem is that well, in small circuits you can compute determinant, of course. That was the first major example. Determinant has a small ABP, that we know, but what is hard to say or what we don't know is are there other interesting polynomials or functions in that have small circuits but may not have small ABPs, right? And also when you look at the definition of circuit, it is not clear how can you convert it efficiently into an ABP. A circuit seems to be doing more than what an ABP can do, right? And this was, I mean, this could have happened even for determinant. When we looked at the circuit of determinant, it was definitely not clear whether the circuit can be converted into an ABP in an efficient way, right? It was by chance that we got a small ABP, but completely different argument. So there might be polynomials which don't have small ABPs but have small circuits, right? That we don't know. So we will not attempt this reduction. Something weaker, which is formulas. Let us only focus on formulas. So this is an old result by Benor and Cleve. Which it says that formulas and with 3 ABPs are equivalent models. Always up to poly size, poly blow up. Right, so we instead of studying circuits, general circuits, we will study formulas. So fan out is one, and we'll show that we'll actually convert it into width 3 ABP. Okay, width 3 means that the matrix multiplication is for just 3 cross 3 matrices. Right, which should be a very surprising thing. It is a very surprising thing. So the in those days, I think the motivation for them to do this was suppose in your computer you have only 3 registers, right? So 3 registers means that there is some information, let's say in register R1 and R2, and using that you can compute something and store in R3. So your memory is restricted to only 3 registers. So using 3 registers, what kind of polynomials can you compute? Right, it seems to be a very weak model. So if you try to implement circuits, whatever a circuit is computing in 3 registers, it looks impossible. I mean, even assuming fan in and fan out you can assume 2, but still doing it with just 3 registers looks difficult. So what they showed is that if you have a formula, that all of that can be implemented using just 3 registers. And yeah, kind of I mean, you can find the proof that it cannot be improved. So you cannot do it with 2 registers. So with 2 is not possible, but with 3 is enough. So let F be a formula of size S and we can assume without loss of generality it is of fan in 2, fan out is 1 of course, and what is the depth? Depth is log S. Why can we assume that? That is by formula depth reduction, right? Brent's proof basically. Okay. So let us now implement this using 3 registers or 3 cross 3 matrix product. So whatever you will do in one step with 3 registers, that you can see as a kind of matrix transformation, and when you do other thing, then it becomes product. So this sequence of this iterated matrix multiplication is really all these operations you are doing on 3 registers, and in the end you want to compute the polynomial. So we'll do it by induction. Okay, we intend to compute f by iterated matrix multiplication of 3 by 3 matrices using bottom up induction. Bottom up means that in the formula start with the leaves and then go to the root. So we are moving upwards and the leaves are here. Okay. So what is the base case? Base case is your gate is simply a variable or a constant. So you may also have a constant here. So gate E, which is either a field constant or a variable. So this gate can be computed as the matrix can you guess? Because I cannot guess. Yeah, so it is basically, it is not just the base case, but it is the whole representation that we want to fix, right? So so in the formula there are these gates, addition multiplication gates are there, and what we are saying is we'll start with the lowest gate and then we'll slowly move upwards, covering the gates in a layer and then move upwards. So whatever a gate is computing, that should be written as some matrix, right? I mean, it will be a matrix product, but then what is it that the matrix product computes? It computes one single 3 by 3 matrix, and which entry in the matrix is your polynomial computed at that gate. So we actually want to fix that representation here. So to make the proof work, we'll fix this representation. Okay, so it's basically the identity matrix with your polynomial E sitting at the corner. Okay, there are 2 corners available, so we have picked the bottom one. Okay, so this will be the representation of a gate, in fact, at any point of time. In any intermediate step, the invariant would be that when I look at the matrix corresponding to this gate, and this gate is computing polynomial E or expression E, in the matrix that E would be sitting here, okay, in the 3, 1, in the bottom left corner this E would be sitting, and we will get a matrix product that computes this. So that is the base case. So you can put variable or constant here, whichever gate you are at in the leaf. Maybe I should also write the idea in terms of register. So register idea is so this is kind of the transformation that if I have 3 registers R1, R2, R3, what this is doing is it will not change R2, R3, but it will use them to change R1. And what will R1 become? It will become this, right? So this the I mean, if you want lower level implementation of this, what it is doing to 3 registers is that it uses the last 2 registers, and in fact it uses the last register R, scales it up by E and then adds to the first register. Okay, this you get by multiplying this matrix on the right side of your register vector. Okay, so this is just right multiplication that gives you this. Is that clear? I mean, this is not very important, but maybe gives you some kind of an intuition. And as you are assuming that a register stores a polynomial in this case, right? So it is actually storing a function. It is not storing on, off, or 0, 1. Right? This is the algebraic model. So here a register actually stores a function. So it starts. So you start in the register with simple functions like x1 or 10, and then using transformations which are also very simple, you will slowly build complicated functions in a register. So it's a very natural thing to do in this sense. So now let us go above the base case. So the first thing is addition, right? Suppose you have an addition gate in the formula, feeding in E1, E2. So this can be computed as, right? So our representation for E1 and E2 are fixed, right? So E1 will be 1 0 0 0 1 0, E1 0 1, and E2 would be computed as 1 0 0. So these are the two things for which you have transformation. So you have these two matrix products, and you want to sum these bottom corners. Yeah, so the representation is so nice that the product will give you E1 plus E2, right? And I have no justification except multiply. Just multiply and be convinced. Right, and it indeed works. So E1 plus E2 is E. So once you have matrix products for E1 and E2, then concatenation of that gives you the sum. So in the intuition of registers, the registers will first work hard to compute E1, and once they have computed E1 in the first register, then they will start working on E1 to add E2. Right, it's going from left to right in terms of registers. Okay, and finally product. Right, that's even more complicated. So how do you compute E1 times E2 using such matrices? So again, E1, E2 is given to you as before, and you have already done the only thing you could have done, that is multiply, right? So what else can you do to get E1 times E2 now in the bottom left corner? Sorry? No, all you can do is multiply and use kind of these symmetric operations. Yeah, so one thing you have to remember is once you have this matrix corresponding to E1, since you have 3 registers, right, you can shift your focus. You can say that, okay, I rotate the registers. So R2 becomes R1, R3 becomes R2, and so on, right? And then the matrix will also correspondingly change in a simple way.
That's also just multiplication, right?
Sorry.
That's also just multiplication by a different matrix, right?
Right. So once you have this even matrix, you also have these kind of symmetric or analogous matrices are also there, where you change your point of view. You call the okay, now this is the second register is my first register, and third is second, and first is third, and so on. So those matrices are also there. So what you have to wonder at this point is, well, I can maybe use some of those and the corresponding ones for E2 and multiply them. Right, and if you think about this hard enough, it will work. So you will get this. Okay, so these are the four matrices. This one, I mean, you are basically interleaving the E1 variants with the E2 variants, right? And can you see that each of these variants is essentially of the same form as the base case, right? So for example, if you look at, right, so if you look at this one, the second one, right, you can ask the question, oh, this is not in that representation, so E1 should have been in the bottom left corner, but why is it in the middle? So how will you explain that? Well, so right, or let us just say see at the register level, because that will be very easy to see. So what this is doing is it is keeping R1 the same, right? R2 plus E1 R3 and R3, right? So instead of putting values in R1, it is actually putting values in R2, but they are of the same type. It is actually multiplying something else, which is R3, with E1 and then adding it to R2, right? So it is just a permutation of R1, R2, R3, but the algebraic operation is the same. It's an analogous operation, and that the same thing holds true for the other three also. What about the minus sign? How do I explain the minus sign? So if you have E1, how do I get minus E1? This should be inversion, right? Then you get 1 by E1, yeah. So how?
You can probably do it like by first swapping rows and then scaling by like this -1 thing, and then swapping rows and scaling it again. Probably just the tedious.
No, it's not. No, but at the register level, somebody tells me how to add E times R3. How do I learn minus?
I mean, each of these operations is just multiplying by to the left and right by permutation matrices, right? So all of those are legal operations. You can just expand out this 4-way product as like an 8 or 9-way product, where you use your representation matrix a few times, and then the other matrix are these symmetric matrices. So then it's just a matrix multiplication, but instead of a 4-way, it's a many-way. So then that way you can, I mean, it is some work though, because to get the -1, you'll have to do like at least 3 matrix multiplications, I think. And one of those, I mean, a couple of those will be multiplication by something like minus 1, 1, 1 or something.
So how are you achieving it by 3 matrix?
Yeah, you should work that out.
Yeah, so this sign still needs some work. So that maybe I'll mention it next time. But these two we have covered.
So will it be wrong to say that it is like R1 minus E2 R2 or something like that?
No, that it is, but then given a long matrix product for E, how do you get one for minus E?
Oh, so you can first multiply the first column by minus 1, then
Okay.
the last row by minus 1,
Mm-hmm.
and then the entire matrix by minus 1.
Yeah, okay. So that is the solution. Yeah, that is the solution.
That won't work, because in the middle one it should be minus 1. Then again the middle column by minus 1. But you can do it, like it's
Yeah, yeah. Okay, so fine. So let us do it. So this one is how do I interpret this one? So I interpret it as follows. Let us. I mean, this you have already seen that I can get to this point. From E2 I can get to this. I will just permute R1, R2, R3 and I will get to this. But now I want to scale it, right? So what I will do is I'll first scale the second row. So how do I scale the second row? By minus 1. I want to multiply the second row by minus 1, right? So
First column and first row.
so I'll do this.
oh yeah, that's the previous one.
So this has a scaling effect on the second row, and now I will scale the second column.
I think what he's saying is the.
Yeah, it's equal.
Oh, okay. Oh, there's many ways.
Yeah, that's why we should do it. So second row and the second column, when we scale simultaneously with minus 1, magically we see that it only changes E2, right? So you get minus E2. So that's the thing. Yeah, so this actually is a slightly different calculation. It's not just register permutation, but also these simple scalings. Fine. So from E2 we can get to minus E2, and then we can put minus E2 wherever we want, at least up to permuting the registers. Fine. So each of these can be produced, each of these 4, and what is the product? Right. So the product will be, yeah, let us multiply the first 2. And then the last 2. Right, and this will be so believe it or not, you will get this, right? So even E2 you will get in the bottom left corner when you multiply these 2.
Why didn't we take two matrices, like if we take E2 to be in the position like 2, 1?
Sorry, E2 in 2, 1.
Yeah, let's suppose there is a matrix in which
E2 is here, okay.
and rest everything is same, like diagonals are 1, 1, 1 and the
Diagonals are 1,
yeah, it's just
okay, and
and
rest is 0.
this is a 0
Mm-hmm.
and the second matrix to be like 3, 2 to be E1.
Yeah, if you do those calculations, you will get this intermediate one of the matrices I have written.
Why do we need those negative E2s and E1s over there? Like we can always have these kind of permutations in which we get a matrix where at 2, 1 we have E2 and 3, 1 we have E1.
No, are you saying that the signs are unnecessary?
Yes. I mean, why do we need those signs?
Why did I put signs?
Take the product of
No, but the sign is needed because look at the second row with first column multiplication. second row with first column multiplication needs minus E2 plus E2 to cancel them. And also look at the third row with second column. That also needs E1 minus E1. So yeah, so I mean you can consider all the ways. Now you know what is the space of ways, and trust me, only this one will work. Right, so fine. So now it's amazing that once you have a matrix product for E1 and a matrix product for E2, using some complicated transformations, you can also get a product for a matrix product for E1, E2, where E1, E2 sits in the bottom left. Okay, so that is the hardness. So this product case is actually harder than the addition case, because it's very hard to get multiplication only in one entry of the matrix. The other entries remain untouched. It's only this one entry which is being, yes. So size analysis, right? So that was, so these are the induction steps. You will do it again and again. For every gate when you do this, this is actually blowing up the size by 4 times, right? So that should give you 4 to the s, which is bad. So how do you analyze this properly? Well, do it by depth. So in one level, actually it is giving you 4 times. So the previous level, the bottom level, you, let us say you have produced the values of all these gates, and when you go to the next level, that size will blow up 4 times.
But then we can't control the width, right, of the RLC?
No, 3 by 3. This is 3 by 3. We never use anything other than 3 by 3 matrix. So width is fixed by design. The only, we are talking about the length, how many matrices are being multiplied. So when you go from one layer of the formula to the next, then the length of the matrix product becomes 4 times, basically because of this E1 times E2. 4 to the, yes, exactly. So what you get is iterated matrix multiplication for 1 0 0 0 1 0 and formula F 0 1, right? This can be factored can be found by induction. And the second thing is size is, its size is 4 to the depth of the formula, which is 4 to the log s, which is poly s. Okay, so this matrix with the formula in the bottom left corner, this can be factored into poly s many matrices. They will be 3 by 3 matrices. Yeah, and give you exactly this matrix. So this is your width 3 ABP. Right. So I mean, once you have identified that F is sitting here in the top, in the bottom left corner, you can extract it, because you can multiply by a row vector on the left and a column vector on the right. Right. So this vector multiplication on both ends will actually extract out F. So this is the definition of width 3 ABP. Is that clear? Right. And the practical kind of interpretation is, physical interpretation is that using 3 registers you can compute any function that has a formula. Right. Just 3 registers are enough. It gives you enough flexibility to move things around in 3 register, starting with the trivial case, base case. And there are other beautiful things here. So these matrices, they are all lower triangular and they have determinant 1, right. So these are actually unimodular triangular matrices. So they are all matrices are lower triangular, unimodular, 3 by 3, right. So it's a very special product. So formulas have very special with 3 representation. And yeah, so that is one way. We have converted formula to width 3 ABP. So tomorrow we will do the converse. That will be the actually, it's almost obvious how to do that. It's an easy solution. And then we will talk more about width 2 ABP.